All right, perfect. So far I've just introduced myself, and is any one of you passionate about physics, or you can also tell if you find physics boring? I'd like to hear. That would be an interesting conversation as well. Is there anyone who finds physics boring?
No.
Wow, that's actually good to know. That's really good to know. Anyone else? Is there anyone who finds physics boring? Actually, that would give me, if anyone says yes, that would give me, what do you call that? An excuse to talk about physics. And I really enjoy talking about physics in general. So, but I think there's no one at the moment who finds physics boring. That's very good, by the way. You should all, because physics is around everywhere. It's everywhere around you. In fact, if you speaking, roughly speaking, you could also say that all science is really physics. Anyways, so with that out of the way, I think we should start with the first topic. It's a very basic topic of measurements. And so I have been covering this topic before, but I think everyone in the class at the moment is, let me just check. Yeah, so all of you are new people. So let me just get your names. Okay, perfect. Right, so we'll be starting measurements. It's a very basic topic, and you can also let me know. You can judge by this lecture how I'm going about it. You can let me know if I'm moving forward too slow or too fast. Both cases, just let me know, and I'll gauge the speed of my lectures accordingly. So is anyone over here appearing? You're all appearing in October, November this year?
No, sir, in May, June.
No.
Okay, so is everyone May, June then?
Yes.
Okay, right, perfect. So I think that gives us some time. So we can do things in a rather more, what do you say? I just use the word a deep fashion. So we'll cover things properly. So none of you want me to go fast, right?
Yes, sir.
Okay, perfect. But it turns out this first topic is a relatively easy one, so this one will be over pretty quickly. You've all taken your O levels as well, so I don't think that you would be having any problems understanding this topic. We'll just quickly go through it. So it involves units, SI units, quantities, errors, in your measurements, scalars and vectors. What are scalars, what are vectors, and how do we add, how do we basically perform their algebra is what I like to call. So anyways, any idea of a physical quantity? What in your opinion, what would be a physical quantity? Anyone? How would you define a physical quantity?
It's a quantity that can be measured.
Which can be measured physically.
Right. Anyone else as well? Okay, so yes, you're right. It's any quantity that can be measured, or as I like to say, that physical quantities are those which are those type of you can say quantities which help in writing down the laws of physics or laws of nature. So for example, consider that you have a block and it's lying on a flat surface, any surface for that matter. And now let's just say in a layman language, you were standing over here and you have pushed this block, right? So you push this block from this direction. Now something will happen to the block. and the block would move. So it would move over here. Let's say it moves this amount over here. At the moment, you're not aware of anything. You're not aware there's a force, there's something called distance or displacement. Let's just forget all of that for a moment. So now this thing happened, something happened when you pushed the block. You saw that it appeared that the block moved a certain amount, right? Now, to understand the physics of what is happening, to define a law, what happened over here, you need some variables. So you define a variable for push, and you call this variable force. Now this force is a physical quantity. Similarly, in the same way, you can define a variable that is assigned to this movement of the block, and you call it displacement or distance, right? So displacement is just a directional form of distance. So let's just call it d. Now d is also a physical observable, or you can say it's a physical quantity, right? And this quantity measures the amount of motion, or you can say the amount of distance that was covered by this block because of this force, right? So these are your physical quantities. You can think of physical quantities in this term. So this was just an example of the idea of physical quantities. Now, of course, we have these physical quantities can be divided into a group of two. We have base or basic quantities, and then we also have derived quantities. Now, basic quantities are those which are, okay, I'll give you an example. It's considered that you were about to make a pizza. And so you would prepare it, you prepared the dough at first, and the dough would act as a base. And everything that you need to prepare your pizza from this point, you would add onto this dough, right? So this base was the most fundamental thing that was required to make anything out of your, to make the pizza itself, right? Now, these base quantities are like that. So they are not, these are the quantities which are not written in terms of any other quantity, you could say. So they are independent and they're alone themselves. So we have length. Length is a physical quantity, and the units to measure length are meters. So of course you say that something moved. It moved 2, it moved 5, it moved 6. But we need to define something that how much of 2 did it move? What of 2 did it move? So how much is defined by 2, and what of 2? So that's meters. So we add 2 meters. So it moved 2 meters. Now, wherever we have meters, it means that we are talking about length, right? And similarly, 5 meters, 6 meters. And in the same fashion, we can talk about mass. Mass is, well, it's the amount of stuff. You could, loosely speaking, you could say it's the amount of stuff in something. But then, of course, I said loosely because you could also go on and ask me, what is stuff then? The mass is just, I'm not going to go into the philosophy of mass, but it's just given, the real thing is really the energy. But we'll not go into that, right? So mass is measured in kilograms. So these are the symbols. So I'll not go in all of these quantities. I'm sure you're aware. Is anyone who in this class right now who is not aware of these quantities? I don't think anyone would be not aware of these quantities. But
I'm
is
not
there...
aware of luminous intensity.
Oh, right. So the last, you could say that these ones, right? So you're not aware of this thing. We are not going to focus at the moment on these 4 things. We'll deal with these. We'll deal with their definitions and where do they come from and all of that in the further chapters. So, for example, amount of substance will be dealt in the thermodynamics part. you can say, or the kinetic theory of gases and so on. Similarly, temperature would also be dealt in there. Current would be, we'll deal with current in electricity and magnetism or electromagnetism, and luminous intensity would be dealt with in optics and optical physics, basically. What we will be looking at mostly at this point would be length, mass, and time. And it turns out that you can make bunch of quantities with only these three quantities. And what I mean by that bunch of quantities is that they are derived quantities. You can derive your quantities using only, well, at the moment we are talking about only these three. These three are going to give you lots and lots of quantities, as it turns out. So, so is the idea of base quantities clear at this point?
Yes.
Right, perfect. So we can move on to derived quantities, and they are written in terms of your basic or base quantities. They can be written as products of base quantities, as a division, or you could say quotients of your basic quantities as well. So for example, you have this thing, which is area. Now, you're all aware of this thing that in one dimension, we define length. In two dimensions, we can define area. And the analog of area in three dimensions is volume. Is everyone, does everyone understand this thing?
Yes, sir.
Okay, perfect.
Yes.
So that's good. That's good. Okay, so it's just area and volume. These are just the analog of length in higher dimensions. So you could even have a 4-dimension space, and there you would be talking about hypervolumes, and but that's not the scope of this course. Okay, so you can make area out of lengths. So x is also a length and y is also a length. Then the units would be assigned as meters and meters. And if I combine these two, if I need the area of this whole thing, then that's just x times y, which would give you meters times meters, which is meters squared, right? So that's clear, right? Now, this meter squared is a derived quantity. There are two base quantities, and two base quantities made up this meter squared. So it's a derived quantity. It's not a base quantity, right? In a similar exact same way, you have volume, which is made up of x, y, and z. Each corresponds to a meter. And so you'd have meters times meters times meters, which gives you meter cube. So that's your volume. And then we have a lot of derived quantities. This is density, which is measured in rho. It's the symbol, it is not measured in rho, I'm sorry. It is represented with the symbol, which is rho, RHO. And the expression for density is mass per unit volume. We'll get into all of these terms in their respective chapters, basically. But so far, it's just, we are just talking about units and these quantities. So the units for that, this would be mass is measured in kilograms, which is an SI unit. Volume is measured with meters times meters times meters. So it's made up of a SI unit, but as you see that you can write down derived units in terms of derived units as well, which is actually pretty trivial, right? So kilograms per meter cube is are the units for density, and so on. So is there any question for derived quantities? I'm not going to go into all of these derived quantities one by one. If you want me to, I can, but is it I think it's very obvious at this point, right? If it's not, you can always let me know. Any question or anything?
No, sir.
No, sir.
Okay, perfect. So here we basically have more derived quantities. We have force, pressure, and these are all written in terms of other quantities. And so they are derived quantities. There is a printing error at this on this page at this point. I'll try to get this fixed, but that's how it is. These are just some of the examples. At this page, we only have one of the quantity, which is resistance. And here are some units for resistance, which are now it turns out, for example, let me actually give you an example over here as well. And I'm sure you're aware of it, but let's just do it anyway. You have force, it is mass times acceleration. So the net force, or the sum of all of the forces acting on a system, is equal to mass times the acceleration. Now, if I were to write down the units for force, that would be the units for mass times the units for acceleration. So the units for mass is kilograms, and acceleration, well, we all know acceleration is the time rate of change of a velocity, but velocity itself is a time rate of change of displacement. So I have this something that looks like this, and if I put the units in this thing, x is meters, it's a length, time is seconds, and then I have this thing, so this gives me meters per second squared. So the units for acceleration are meters per second squared. So I'll just put that over here, meters per second squared. Now this is a unit for force, but what we do in respect to the scientist, for respect to Sir Isaac Newton, we give these, this unit is given a name, which is called newtons, right? So it's Newton. And hence, it's the symbol for this is actually N, and force is measured in newtons. Now saying newtons just means kilograms meters per second squared. In this, in the same way as 1 + 1 means 2. So whether you say 1 + 1 or you say 2, they're both the same thing. Anyways, so is there any question at this point?
No, sir.
I'm sorry, you said no, right?
Yeah.
Okay, perfect. Okay, so there is no question at this point, so we'll move right. So basically I did carry out this class. I'll just get rid of some of these things so we can do them. We can do them from start. Just let me get rid of this as well. All right, so now we'll talk about prefixes specifically. So what are prefixes? Any suggestion or anything that you would like to say about them? What do you think? What are prefixes? Okay, so prefixes are, well, first I'll tell you why do we even need something that's called a prefix. Prefixes are really there to make your life easy. You just have a number. I'll write at this point on top over here. Suppose you have a number that reads 1000. Now, instead of writing 1000 every time, because in physics at later point you see that you'd be, when you're performing your workings or calculations, you'd be repeating numbers quite often. So it's better to assign a prefix to something that appears normally. So 100 would appear normally, 1000, 10,000, and so on, right? So for example, you have any number that comes with 1000, you just assign a prefix kilo to 1000, and then you can write it as K, right? So K is just a symbol for kilo. Now, the idea behind this is similar to the idea behind 7x. what do you think is happening? Algebraically, what is happening over here? 7x, what is this? It's just algebraically, it's just 7 times x, right? Everyone agrees with that, right? So
Yes.
exactly. So for example, I have a number 2, and let's say I have kilograms. Now, sometimes it is that it's some people find it hard in converting units as well. So prefixes also makes that easy, because this is 2 kilograms. Now the same thing is going to happen which happens over here, 7x. So 2 is like just this number, and k is behaving as x, so it's 2 times k, and then you have grams. Now k is a prefix, but what was k? K was 1000. So I'll just replace that, and this becomes 2 times 1000, and then grams, and so that's 2000 grams. Right? Now, in exactly the same way, you can do for centi as well. I'm sure you're all familiar with centimeters, for example. So we know that one, or let's just say that centi, now it's a number that's 10 raised to power minus 2, which is just 0.01. This number is basically represented with C or centi. Now, what does that mean? That means that if I have 1 centimeter, so if I'm writing a unit of length, so this is length, right? C does not have anything really to do with length, it's just a prefix. And then I can write this as 1 times, and the value of C is 0.01, and then you have meters. So this is 0.01 meters. And that's why we say that 1 centimeter is equal to 1 over 100 meters. So is this clear? Is there any question from this thing?
No, sir.
It's all
It's clear, right?
Yes.
So you right, amazing. So you have different prefixes. You have pico, nano, micro, milli, centi, and these are all prefixes. And again, they're all here to make your lives easier. Now, before I proceed, let me just check how much time do we have left. Okay, we have around about 8 minutes left. So are you okay with the speed so far, or do you think it's too slow? Specifically, even for this chapter, I think it might be too slow, but what's your opinion?
I think we can go a bit faster.
Okay, right, perfect. So we'll do this next topic, where it's a topic of making estimates, right? Now in physics, well, in general, you would find yourself making estimates normally, and your estimates are given to 1 or 2 significant figures. Now, the more significant figures a number has, the more accurate or precise the value is. But because we're giving estimates are not really they're not really accurate. So for example, if you were to make an estimate of 3 cans, the mass of 3 cans, you could say that a reasonable estimate is 1 kilograms. 3 cans of Coke, which are 330 ml, would weigh about the mass of them would be 1 kilograms. And so these are all estimates. And so for example, let's see how do we work with estimates by looking at this example over here. So it asks you to estimate the average running speed of a typical 17-year-old's 2.4 kilometers run, right? So we'll have to make some estimates in this problem. First of all, we'll start with the expression for average speed. So we know average speed is simply given as speed is equal to distance traveled or divided by the time it takes to cover that distance. And well, what we have over here is 2.4 kilometers. So, okay, I know this 17-year-old person is running 2.4 kilometers. But we have to make an estimate for the time. So what would you, well, it's a very rough guess that you would have to take over here. It's a 2.4 kilometers run. Normally, a person who's active, or you can say lies between active, or so it's an average runner. 17-year-old is a very young age as well. So you could say that it takes anywhere from 10 to 15 minutes for this person to complete the 2.4 kilometers run. It would take around 10 to 15 minutes. And so we have two values, right? So if we find an average value of these two values, you get 12.5 minutes. So 12.5 minutes. So I can just write here 12.5 minutes. Now, all you have to do from this point is just convert. If the question does not ask you to convert or write it in meters per second or kilometers per hour, but again, you cannot write it in kilometers per minute. That's not really a reasonable units for speed. So we'll convert it into meters per seconds. For example, let's convert it into meters per seconds. Let me get this thing a bit over here, make it small. So now to convert it into meters, it's very easy because we have 2.4 and we don't need this K over here because we only need meters. So we'll write the value for K. So that's 2.4 and multiplied by K is 1000. And then you are left with this meters. Now divided by 12.5, what is minute? We know minute is defined as 60 seconds. So in place of minute, I can just write 12. This 12.5 is actually being multiplied with minute. So it's multiplied by, in place of minute, I'll write 60 seconds. So if I do some cancellations and so on, I get something approximately I think 3.0 or 3 meters. Yeah, 3 meters per second, right? So I don't think that there would be any problem with this thing as well. We just made an estimate for a person, anyone who's quite young and is running a 2.4 kilometers race or run, and we estimated some time that it would take for this person to run, and we got our answer, right? These questions are typically given as MCQs, and over there, the answers have a lot of difference in their values. So if you can even make an estimate that is almost as good, it works out in MCQs, right? Making estimates. So you don't have to worry about making an exact estimate of 12.5 minutes. It could be, you could have taken 15 minutes. You could have even taken 20 minutes, right? The answer that you would guess would be closer to only one of those MCQs, and then you can just get your answer from there. So that's clear?
Yes, sir.
Yes, sir.
Okay. So we have some, it's clear, right? For everyone?
Yeah.
Okay, so we have some more problems over here. These are also here to make estimates. I should have gotten rid of all of these workings that I did in the last class before, but I did not know that everyone who would be appearing in today's class would be new, so I'll just do all of this thing again. 1 second. Okay. So here we have an MCQ, and it says which estimate is realistic. So how do we go about this problem? Well, of course, we'll first read the options. We have the kinetic energy of a bus traveling on an expressway is 30,000 joules. So let's see if that makes sense. So we have a bus, and let's suppose that the mass of the bus, let's just say that it's some m, and if any bus that normally travels on an expressway, it travels around about from 50 to 100 or 80 kilometers per hour. If I convert this, now I'm sure that you're very familiar with the conversion, so I'll not go into that again and again. If I convert this, it becomes 13.8 to 22